Hello and welcome back to Complex Analysis. And of course, first I want to thank all the nice people that support this channel on Steady, via PayPal or by other means. Now, today in part 11, we will prove the important result about the uniform convergence and power series from the last video. In order to do this, let's quickly look at the statement again. So we have a power series named f defined on the open disk of convergence. Then we are able to show three important statements here. The first one is that inside the open disk, for any closed ball, we have the uniform convergence. Next, the second statement tells us that this property also holds for this formal derivative. And then in the last step we can show that this is indeed the derivative of our power series f. Or in other words, f is complex differentiable for any z, and the derivative is as we expected. Now, I already told you this is an important result because it tells us that every power series is a holomorphic function. And for this reason, I think it's very helpful that you can see that we can actually prove it. The proof is not so complicated, and indeed only part 3 will take some time. However, also for the other two parts, to make our life a little bit easier, let's assume that the expansion point z0 is equal to 0. This is not really a restriction because the general case would work exactly the same. In the end, this is just one translation in the complex plane to get any other expansion point. Still, for us here, everything is tidier and clearer when z0 vanishes from all the equations. Okay, knowing this, let's start with the proof of part 1. There we need to show a uniform convergence, and therefore we consider the difference f minus fn in the supremum norm. Here, of course, fn is just the polynomial given by the partial sum. Also, please note z0 is set to 0 here, and this one is our domain. Which means we have a closed ball inside the domain of convergence. Of course, this is how you should understand the supremum norm here. It's the supremum norm with respect to this domain. Hence, we can immediately write this down as the supremum where z goes through all the points of this closed ball. And it's applied to the absolute value f of z minus fn of z. Which is of course simply our power series that now starts with n plus 1. Simply because we subtracted the terms from 0 to n. Now, this is something we can work with because for the absolute value we have the triangle inequality. Now, in order to apply it, we first have to pull this limit here out of the absolute value. This is possible because the absolute value is a continuous function. Okay, then the triangle inequality just means that now we have the absolute value inside the sum. So we simply have the absolute value of ak times the absolute value of z to the power k. So what we can use now is that the point z lies inside the closed ball with radius c. Hence the length of this point, the absolute value of z, is not greater than c. So we know we have a nice bound here. This is less or equal than c. Okay, so this is a nice result because now we can omit the supremum here because there's no z involved anymore. Hence, what we get is a power series that starts with n plus 1 of the absolute value of ak times c to the power k. And now you might already see this looks close to a geometric series. And indeed, we can use a geometric series as a majorand here. And please note here, because there's the absolute value involved, we are only working with real numbers now. For this reason, you might recognize the whole argument here from a real analysis. Still, I really think it's helpful that we discuss it here. Okay, now the last step here I want to put as a remark on this side. By assumption we know that this power series is convergent because the real number r tilde here lies in the region of convergence. So the point here is we can choose a number that lies between c and r. So what we know is this series is convergent, hence the sequence inside has to be bounded. Hence we find a bound we can call b such that the absolute value ak r tilde to the power k is bounded by b. Now, the left hand side we can simplify because r tilde is a positive real number which does not need the absolute value. Therefore, in the next step we can write this as b is greater or equal than ak in the absolute value times r tilde to the power k. Okay, and now you see we have to bring c to the power k into the game here. Of course, we can just do this in this way, but then we have to divide by c again. Hence, what we have here is the factor r tilde divided by c to the power k. And here you see, this number r tilde divided by c is a number that is greater than 1. Therefore, we can call this number q to the power minus 1. Hence then, q is a number strictly less than 1. Okay, and now you see, this whole thing here we can use for an estimate of this part there. This is now simply less or equal than b times the series of q to the power k. And there you should see, this is just a very nice geometric series, which is of course convergent because q is less than 1. This means when we send the lower index n to infinity, this whole thing goes to 0. And exactly this is what we wanted, because it means all the terms here are 0 in the limit. Hence, the supremum norm goes to 0 and we have the uniform convergence. Okay, there we have it. The first part is proven. Now, fortunately, the second part can be proven with exactly the same steps. And in order to see this, let's go back to the statement. So you see, it looks exactly like part 1, the only difference is that we have another power series. Or in other words, we just have other coefficients, but these don't change the argument here. Therefore, the only thing we actually have to check is that this power series has the same radius of convergence like the first one. And this is what we can do using the Cauchy-Riemann theorem. So please remind yourself, this is just one limb soup we need to calculate. For this, please note that our new coefficients for this power series are given by ak times k. Or more precisely, we can give it a name and call it bk-1. The index is k-1 because the power here is also written as k-1. Okay, and now you know, for the radius of convergence, we need to calculate this limb soup for k to infinity of the kth root of the coefficient in the absolute value bk. Hence, what we have inside here is ak plus 1 times k plus 1. Okay, when we have this, I don't have to go into the details because you see we can split it up into two parts. The first part, where the coefficient ak is involved, gives us the original radius of convergence r, and the second part just goes to 1 in the limit k to infinity. Therefore, the radius of convergence of this new power series is simply the same as we had for the original one. And this means we can simply redo all these steps, but now instead of ak we would write bk. So I would say that's enough for part 2. The interesting proof is indeed part 3. For this reason, let's invest the next minutes to calculate the derivative of our function f. Of course, what we want to get out is that the derivative is given by this power series. Hence, we need a good name for this function. Let's call it f tilde. So in the end, we want to get out that f tilde is actually f prime. However, at the moment, we don't know if f prime exists. Therefore, we are not able to assume it, we have to show it in this proof. However, of course, we can look at the difference quotient. This can be written as f of z plus h minus f of z divided by h. Obviously, here h is also a complex number, and in the limit h to 0, we get f prime of z. For this reason, a good idea would be to subtract f tilde of z. Then the thing we want to show is that this term here goes to 0 when h goes to 0. And of course, in order to do this, we also will use a triangle inequality. But before we do this, let's split our power series f into two parts. So you see here, instead of f, I write it as the sum of Pn plus Qn. Hence, the idea here is to take the infinite sum and to divide it at the index n into two parts. More precisely, this means Pn of z is given by the polynomial that ends with the index n. Accordingly, Qn is simply defined as the whole rest that starts with n plus 1. Now, the reason why this splitting here can be helpful we have seen above. The derivative of the polynomial we can immediately calculate. And exactly this derivative of the polynomial we want to include here and then use the triangle inequality. However, before we do that, let's first put Pn at the front and Qn at the back. So here's the difference quotient with Pn and there is the difference quotient with Qn. Of course, we still subtract Fn, but here we want to add and subtract the derivative of Pn now. Hence you could say we have simply added a 0 here. Okay, now you should see that this really helps because now we have three different parts here. Also, you surely remember our goal is to apply the triangle inequality. So what we have to do is to take the absolute value on both sides. Okay, then you should see this really helps us because now we can separate the three parts in the absolute value and get the inequality. Now, this is very nice because we can give the parts names and talk about them separately. Of course, we don't need fancy names, so maybe we call the first one simply A, the second one B, and the last one C. So then let's see which one of them makes problems. For the first one A, we already know when we send h to 0, this one goes also to 0. Hence, no problems there. What about the second one? Indeed, by the property 2 from above, we already know this thing here converges to 0 when capital N goes to infinity. This is simply because the uniform convergence implies the pointwise convergence we have here. Of course, in this case, the question remains what happens with the last part C here when N increases. If this one went bigger and bigger, it would not help us that the first two ones get smaller and smaller. Therefore, we have to analyze part C in detail. First, I would say inside the absolute value, let's substitute Qn again with the power series. Hence we have one part with z plus h and one with just z. Then, of course, we should put both terms together. So we simply have the series with ak times z plus h to the power k minus z to the power k divided by h. Now, this looks much simpler than before, and indeed we can simplify this even more when we use the geometric sum formula. Indeed, this one is applicable because we have the same power and the difference involved. To refresh your memory, the geometric sum formula holds for any number q, and it looks like 1 minus q to the power k divided by 1 minus q. So you see, there is one exception for q. Q is not allowed to be 1. However, in all other cases, this is indeed the finite sum starting with 0 and ending with k minus 1. And we simply sum up all the powers of q. Now, in order to apply this formula here, the trick is to use a suitable q. Maybe not so hard to see is that we need both z plus h and z in q. Hence, what will work is when we choose q as z divided by z plus h. Then we can just multiply on both sides with the correct numbers such that the left-hand side here looks like this. Additionally, and I simply tell you this now, we find that the right-hand side has a very nice form. We start with the highest power of z plus h, which is the power k minus 1. Then the next term in the sum is z plus h to the power k minus 2. However, then in addition we also find z to the power 1. Hence we can say here in the first term we had z to the power 0. So you see, this whole sum continues until we reach the last term, z plus h to the power 0 times z to the power k minus 1. Now, please don't forget, this whole sum here is only the part inside the series after ak. This is important because you know we apply the absolute value on the whole term. Of course, then we can use the triangle inequality again. First, we use it here to push the absolute value inside the series. And then you see, for this whole sum here, we can use the triangle inequality again. Indeed, what we can use there is the fact that both z and z plus h lie in our ball. Hence we know the number r is an upper bound for the absolute value of both numbers. So you see, for the absolute value, we have r to the power k minus 1 here, here, and so on. And because the sum has exactly k terms, we know we have this k times. In conclusion, we get a very nice inequality now. Of course, we still have the series and the absolute value of ak, but then comes r to the power k minus 1 times k. And that's a very nice series we get here. So you see, this is related to the derivative we already considered in part 2. And then you should see I need to correct myself here because we need to lie inside the domain of convergence. Hence, in order to do this correctly, we need to choose a number r tilde, which is less than the radius of convergence r. This is no problem at all, because z and z plus h lie inside the domain of convergence. Hence, instead of the number r, we can choose a smaller number r tilde as the bound for all these numbers. Then we get this series here, and the most crucial fact is this is a convergent series. And therefore, this tail of the series has to go to 0 when capital N goes to infinity. Okay, and with this you see, we have complemented the last missing part of our estimate above. To make it clearer, I would say, for the end of the video, let's go through the argument again. So we start with a fixed point z and a small h. Then I just give you an arbitrary epsilon greater than 0. And then you simply choose n so large that this part and this part are both smaller than epsilon. After this, in the last part, we simply take the limit h to 0 on both sides. Then a will vanish and we have the fact that this limit here is smaller than our epsilon. To put it in other words, the limit is arbitrarily small and therefore the limit has to be 0. And there you see, this concludes the whole proof. Well, I still hope after this technical proof you are still interested in complex analysis. The next video will be easier when we just look at examples for power series. So I see you there and have a nice day. Bye.